One of the boldest questions in space exploration is simple. How close can a spacecraft get to the Sun? For most of history, the Sun was too bright, too hot, and too violent to study up close. We could watch it from Earth and later from orbit, but the region where the solar wind is born remained difficult to reach. That matters because the Sun is not just a glowing object in the sky. It is the engine that shapes space weather. Around Earth affects satellites and fills the solar system with charged particles. NASA's Parker Solar Probe was built to answer a question that sounds almost impossible. What is happening in the Sun's outer atmosphere close to the source? Instead of staying safely far away, Parker follows a path that brings it repeatedly closer to the Sun than any spacecraft before it. The trick is not brute force, it is careful engineering. The spacecraft carries a heat shield pointed toward the Sun, while its instruments sit in the shadow behind it. It also uses repeated flybys of Venus to reshape its orbit, gradually lowering its path closer to the solar atmosphere. What is known is remarkable. Parker has sampled regions near the Sun that no spacecraft had directly explored before. It has measured particles, magnetic fields, and waves in the environment where the solar wind begins to take shape. What remains uncertain is the full story behind the Sun's most energetic behavior. Why is the corona so much hotter than the visible surface? How exactly does the solar wind accelerate? Parker is not a magic answer machine. It is a messenger, from a place we could once only observe from a distance. The takeaway is simple. Some missions do not just visit worlds. They enter environments that rewrite our idea of what exploration means. And this briefing begins with a spacecraft flying into the edge of a star. The Parker Solar Probe does not fly straight at the Sun. It performs one of the strangest journeys in spaceflight. It uses Venus to fall inward. That sounds backwards. On Earth, we usually think of rockets as machines that push forward, but around the Sun, speed is also a kind of trap. Earth is already moving around the Sun very quickly. A spacecraft launched from Earth inherits that sideways motion. To get much closer to the Sun, it has to shed some of that motion, not simply aim downward. Venus becomes the helper. During carefully planned flybys, Parker passes near the planet and exchanges a little orbital energy with it. The planet is not harmed or changed in any meaningful way, but the spacecraft's path around the Sun is adjusted. Over repeated passes, Parker's orbit tightens, bringing it closer to the solar atmosphere again and again. This is why the mission is so fascinating. Its boldness is not only the heat shield, it is the patience. Parker does not conquer the Sun in one dramatic leap. It approaches through a sequence of orbits, each pass adding more information to the story. The spacecraft has already crossed into the Sun's corona, the outer atmosphere, where magnetic fields and charged particles dominate. There, the usual idea of empty space breaks down. Space becomes a moving sea of plasma, shaped by magnetism and constant outflow from the Sun. What scientists know is that Parker can survive because its design keeps the most sensitive parts protected, while it points precisely toward the Sun. What remains difficult is interpreting the changing environment it flies through. The Sun is active, restless, and never exactly the same twice. The memorable lesson is that a mission can be daring and patient at the same time to reach the Sun. Parker first learned how to dance with Venus, the deepest mystery. Parker Solar Probe is. Chasing is not just heat. It is motion. Why does the Sun constantly send a wind of particles streaming through the solar system? This solar wind is invisible to our eyes, but it helps shape the space environment around every planet. It flows past Mercury, Earth, Mars, and far beyond the outer planets. Most of the time, it is simply part of the background weather of space. During stronger solar activity, it can disturb magnetic fields around Earth and affect spacecraft radio communication and power systems. This is important, but it is not a reason for panic. It is a reason to understand our star better. Before Parker, scientists had good observations from far away. They could see the Sun's surface activity, track eruptions, and measure the solar wind after it had already traveled far from its source. But that is a little like studying a river only after it has reached the plains. Parker is flying closer to the mountain springs. The evidence it gathers helps researchers test ideas about magnetic fields, plasma waves, and tiny bursts of energy near the sun. Scientists think these processes may help heat the corona and accelerate the solar wind, but the exact combination is still being worked out. That uncertainty is not a weakness, it is the frontier. Parker's value is that it connects distant effects to nearby causes. Better knowledge of the sun can improve space weather forecasting and help engineers design spacecraft that survive harsher environments. It also reminds us that Earth is not separate from space. We live inside the atmosphere of a star stretched thin across millions of kilometers. The main conclusion is careful but powerful. Parker has not ended every mystery of the sun. It has brought the questions closer to the source. And the next question is the one every great mission leaves behind. What will we understand when we dare to go even nearer?